Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In a previous video, we saw that one parameter groups of transformations can be studied infinitesimally and have an infinitesimal generator called, which turns out to be a vector field. Now, one of the ways to think about a Lie group, and in this video we'll talk about the Lie group G here, is to think of it as a multi-parameter group of transformations. And then you can ask, well, can you also do an infinitesimal study of it? And the answer is yes. And to do that, we're going to use the notion of the exponential map. Okay, so let's see how that works. Okay, and to do that, we need firstly the notion of what's called a left-invariant vector field on our Lie group G. Okay, so suppose you have a little element G that's inside your Lie group BG. Then we could talk about left translation by G. So what does left translation by G do? Okay, it takes an element of this group H, say little h, and you just multiply it on the left by G to give you another group element inside this big G. So it's an automorphism from G to G. Okay, that's what we have. And now what we want to do is we want to define a vector field on this Lie group for every vector inside the tangent space to G at 1. Suppose here's the identity of the group, okay, and we have a tangent space here, and that tangent space at the identity we denote with this Gothic G here. Okay, so that's fairly common notation for the tangent space to the identity of a Lie group, and we just pick a tangent vector, little v, inside there. So with that one vector, we're going to smear this vector over the whole of the group so that it's what's called left invariant. Okay, so that's going to give us a vector field xv. And how do we define it at a point like this one here? Okay, so that we get an xvg. Well, the way we do it is that left multiplication by g sends 1 to g, so it sends the tangent space here to the tangent space there. So we're going to look at the derivative of tau g at 1 and apply that to v, and that'll get us some vector over here like that. And as we vary the g, you'll get a vector at every tangent space of this Lie group, and hence you get a vector field. And because the group multiplication is smooth, this will actually be a smooth vector field. Okay. And what's really nice about this, and this is the important remark, is that this turns out to be what's called an example of a left-invariant vector field. So what does it mean to be left-invariant? So that means that if, for example, you want to translate, okay, by left multiplication by some element h inside the group, okay, this vector field is compatible with that. How is it compatible? Well, suppose you want to evaluate this vector field not at g now, but at g translated on the left by h, so tau h of g. Well, that's actually equal to what? That's the same as if you start with the original vector here at xvg and you apply d tau h to it. Okay, so that means that if you're over here, well, you applied left multiplication by h on that g, what is the value of the vector field there? Well, you just apply, the value here is you just apply d tau h, so left multiplication by h, and its action on the tangent space will send this tangent space to this one, and it'll be the image of this here over there. Okay, so that's compatibility with left translation. So let's see how that works. It's quite easy to prove, and I'll prove it for you now. Okay, so we'll start from the other end. We'll apply d tau h to this xv at g. Okay, so what was xv at g? Xv at g was you just do d tau g at the identity of this v. Okay, and so now you apply a composite of derivatives. Okay, so you first left translate by g and then you left translate by h, but that is the same as the derivative of the composite function, and composing this left translation by g with left translation by h is just left translating by hg. So this is just d tau hg at 1 of v. Of course, if you look at that, that's the definition that we have here, but instead of a g, we have hg. So that's just xv evaluated at hg. So the value of this vector field xv at hg is the value of xv, not at g, but at g translated on the left by h, tau h of g. And that shows you why that these vector fields that we've constructed very naturally using the group operations are left invariant. Okay, so these are very, very important things, and I hope you can kind of see that actually these are the only left invariant vector fields that you'll get. Okay, they're completely determined by what the vector is at the identity. Once you know what that is, you use left invariance to basically send this over to the rest of the group, and it's predetermined what that left invariant vector field has to be once you've determined what it is at any point, including this one. Okay, so that's very nice. Okay, so what are the nice properties of this vector field? So one of the things you can try to do with vector fields, of course, is you can talk about integral curves to them. Okay, and in this case, because if you decide to do some left translation, basically the vector field goes back to itself. That means that a left translation by any group element, say G, sends an integral curve to an integral curve. Okay, you just left translate, right? Basically, you can carry the whole curve and all the tangent vectors with it, and it'll go back to the same vector field. So that's a very important remark that we have there. I next want to move on to the following proposition, which is going to allow us to set up the exponential map. So the first thing is that this vector field is actually the infinitesimal generator for a smooth R action. We'll call the R action alpha, like we have done in the past videos. So alpha you can think of as a map from R cross G to G. So remember, in general, if you have a vector field, it may not come from a smooth R action. Okay, you may not be able to get the whole of the real numbers to act. And the reason why is that when you set up this correspondence, okay, you need to know that integral curves exist for all times for this to happen. So it may be that integral curves don't happen all the time, but in this particular case, these are super nice and they do exist for all time. Okay, so once we have that, we can talk more about the integral curves. In fact, we can say a little bit more. So we can say that there exists a smooth group homomorphism from the reals to the group, and we'll call this phi v. So we fix the little v, which is this tangent vector here. Smooth group homomorphism. And what property does it satisfy? Alpha t of g is equal to g times phi v of t. Okay, so this group homomorphism that you have here, okay, is defined by this formula that you have here from the R action, from the smooth R action. Okay, so let's kind of see why this is true. The second part is quite easy actually. We can just define phi v of t to be alpha t of 1. Okay, if you put g equals 1 here, that's the thing that it has to be, and you can check that that works. So the more important thing is to see why is it that you expect that these integral curves for this xv are defined everywhere for all time. Okay, so for all values of t, not just some values of t. So that's going to be the thing that's really important. And the way we'll do it is we'll give the picture which explains what's true, and it's the following. So suppose you have an integral curve like this one here, and it's not defined, or you don't know that it's defined for all time. Then what can you do? Okay, suppose it's defined like this for this green time, and you want to extend it a bit further. You want to extend it over to the other side a bit further, past there. But remember what I told you in this remark, okay? The important thing here is that tau g sends integral curves to integral curves. So what we do is we find a group element which translates this point over to this point. So maybe this is g and this is hg. So you can left multiply by h now, and that will move this entire integral curve over like this. And they'll overlap like this. So in fact, the whole thing, when you take the union of the two, so to speak, is an integral curve, and you've managed to extend this integral curve a little bit to one side. And then you can keep extending it for all times. And that's the reason why that these integral curves exist for all time, and hence you get this smooth R action. Okay, so that's really, really great, isn't it? Okay, so now we can actually come up with the definitions that are important for this video here. So firstly, the image of this group here. So this is a group homomorphism, and the image of this group is going to be a group as well, and it's called a one-parameter subgroup of this Lie group G. Okay, one parameter because it's the image of this reals, and that's a one-parameter group. Okay, so that's the first thing. That's called a one-parameter subgroup, and now we can define the exponential map. So what's the exponential map? Okay, so remember I want to do infinitesimal study of the Lie group G. Okay, so infinitesimal means that I want to look at this tangent space to G at 1, which remember is this Gothic G I have here. So the exponential map is going to be a map from this Gothic G, this tangent space at 1, to the group. And what am I going to do? How's it going to work? It's going to be, I take this vector here, V, okay, and remember I have this smooth group homomorphism associated to this one parameter group, phi V associated to it, and I have just evaluated at 1. Okay, so that's the exponential map, but perhaps it's better to think of it pictorially as what's going on. Okay, so let's just go through all the steps of what's going on. We start with this vector, tangent vector at 1. Here's a tangent vector at 1, so that's this one here. And then the first thing is we make it a left-invariant vector field using this prescription that I have here, okay? So we smear it out and we get this vector field, which is all these blue arrows, okay? And then what do we do? The next part is we construct this smooth action, remember, which is just you look at these integral curves to this, okay? So let's build an integral curve that starts at 1, okay? So we go along and build an integral curve like this. And what we do is we travel along for time until you have hit time 1. And at time 1, that's going to be the value of the exponential map. Okay, so this is xv. And that's equal to, okay, you travel along that integral curve for this left-invariant vector field for 1 unit of time. Okay, and that's what you get. Okay, so what's so nice about this? So one of the things is that, well, you can use the theory of ordinary differential equations to study this map. And the first thing that you kind of see is that when you do this, actually, we're starting with this tangent space, and actually, you can say, well, what is the differential of this map? This is going to be a smooth map that follows from the theory of ordinary differential equations. And you can say, what's the differential of this map? Well, here you go from the tangent space to G, well that's the vector space, so that's just this Gothic G, to the tangent space at 1 of G, and that's just G itself, and there's a very natural guess as to what that the derivative of this exponential is. It's the identity, and that's the case, and hence this is a local diffeomorphism. It's pretty neat, isn't it? The other thing is that, well, what about xtv? What is xtv? Well, it's essentially, as t varies, this gives you this map here. Okay, so it's going to be phi v of t. Okay, so it is your one parameter subgroup. And the reason why that is that suppose you just scale this v. Okay, since this is left invariant, okay, basically you scale all the vectors in this vector field by that t. And then if you travel along this at unit time, where will you get to? You'll get to phi v of t. That's where you'll end up. And that's why you have this lovely formula that you get here. So the theory I've presented so far may look rather abstract, but actually it's very concrete in most of the examples that we want to use. Okay, so the most important example we have here is that G is the Lie group GL and R of invertible n by n matrices over R. Okay, so what's the tangent space at 1? So this is, of course, just all the n by n matrices such that the determinant is non-zero. So it's an open subset of the set of all n by n matrices. And this is just a vector space geometrically. Okay, so essentially this is just Euclidean space. So the tangent space is just actually this here. Okay, so the Gothic G here is just the essentially the Euclidean space of n by n real matrices. So now let's pick an element of this tangent space. So that's just some n by n real matrix A, and you can let it generate this left invariant vector field, and you can ask, well, what's the exponential of this a here? Okay, what's x of a? So to do that, we have to look at the corresponding integral curve. And I claim that the corresponding integral curve here is phi a of t is going to be the matrix exponential e to the ta like that. Okay, so why is that true? Okay, so let's just check. We've got this curve here. Okay, we let t vary over the reals. Okay, and you can differentiate that and work out what are all the tangent vectors there. Okay, so let's differentiate this, and what do you get? Well, we know how to differentiate the exponential. Okay, with respect to t, there's a coefficient of a here. So basically, it's just the exponential, but there's an a coefficient, so we have to pull out the a. And the way I'll write the a is I'll write it on the right. Okay. So if you look at what are the tangent vectors to this curve as you vary t, okay, what are they? Well, it's going to be e to the taa. But I claim this is just the value of the left-invariant vector field associated to a, because how do we get that? We start with this a, and we just left translate by the corresponding point where you evaluated at. So we just left translate by e to the ta. So this indeed is the correct integral curve. And then all we have to do is to evaluate the integral curve. You just go along it for time 1 at t equals 1, and that gives you the exponential of a is just the usual matrix exponential. And this is, of course, where the name of the exponential map comes from. Okay, so it's rather nice that this tool that we have from linear algebra. Okay, so this gives us an example of something that's very nice. Okay, this map, and you can see if you put x e to the ta, that's going to give you a 1-parameter group. Okay, that this generalizes to an abstract Lie group. Okay, so that's a nice example and makes it very concrete what we're doing. Okay, so let's do a slightly different example. So we're going to look at a subgroup of, in this case, not GLNR, but GLNC. Okay, but a similar sort of thing will hold. Okay, so in this case here, we're going to look at the unitary group. Okay, so what's the unitary group? You're looking at n by n complex matrices. Okay, A, such that the Hermitian conjugate, so this is the transpose of the complex conjugate, A star times A is equal to I. So A star is the inverse of A. Okay, so what's happening here? Well, we want to look at what's the tangent space to the identity of this group. Okay, and that's denoted by this Gothic U of n. And I claim it's just all those n by n complex matrices B, which satisfy now essentially the derivative of this, which is B star equals minus B. Okay, so that's what does that mean? Basically, these are all the n by n matrices which are skew Hermitian. When you take the adjoint, it goes to its negative. Okay, so there's the skew Hermitian matrices. And it's quite easy to sort of understand why that should be true. This argument here, I guess you can turn it into real proof, but I just want to illustrate the ideas as to why you expect this to be true, and that's by differentiating this condition here, A star A equals I. Okay, and you want to differentiate it at the identity where A equals I. So how do you do that? Well, you start with I, and you just vary it a little bit by a tangent vector, so to speak. So you vary it by some matrix, delta A. So the condition here to be inside this unitary group is that I plus delta A star times the original I plus delta A is equal to I. Okay, so let's expand this left-hand side out. Okay, you get I plus delta A star plus delta A, and I guess you can assume that the delta A star times delta A is going to be small as usual. In the limit, this is going to be 0. So we say that this is approximately I. And of course, cancelling i's from both sides, you can see that this sum here is equal to 0, so that delta A star is approximately equal to minus delta A. And when you take the limit, this will become an equality. So that gives you the condition to be in this tangent space. Okay, so it's a nice argument, and you can see it's fairly computable. And also, the conditions here translate to something fairly natural. Okay, so that's rather nice. And in this case here, you can also take exponentials of complex matrices, and this will give you the exponential map here, except for what happens is that what you put in here are these matrices H which satisfy this property, these skew Hermitian matrices. And when you map it over to its exponential, one of the things that you will see that you will get, and I guess you can check this fairly easily, is that this is actually going to be unitary. Okay, it will satisfy this, and that's quite easy to see that that's the case, and it's suggested by this argument too. Okay, if you're looking for a little bit of a picture of what goes on, the easiest case will be when n is equal to 1. Okay, when n equals 1, what do we see? When n equals 1, we're just looking at, I guess here you'll have your 1 by 1 matrix, so these are just complex numbers here. So it means that the complex conjugate times itself is equal to 1, so it's just all the complex numbers of square modulus 1 or modulus 1. Okay, so that's the circle group. Okay, U1 is just the circle group S1 inside the complex plane. Okay, so where's the identity in the group? So in the Argand diagram, it's just 1 is denoted here. And what's the tangent space? The tangent space, of course, essentially you think of as this line. It's going to be one-dimensional. You can think of it as the reals. But since it goes up and down like this, it's kind of more natural to think of it as IR. And so a tangent vector here you can write as IT. So note that this IT, this is skew Hermitian. Okay, if you take the complex conjugate of this, you get minus IT, which goes to its negative. Okay, so that's why it's good to write it like this, and that's in what sense we're working here. Okay, and now what about this exponential map? So if you just look at e to the it, of course you know that this is a complex number of modulus 1, and that's what we get there. Okay, so there are some good examples. And actually, it's very representative of what you need to know about the exponential map and how it actually gets used in practice. So the other thing is that, well, what does the exponential map tell us? And the key point is that you want to be able to study Lie groups. And so the most important thing is to compare Lie groups. In other words, you want to look at homomorphisms of Lie groups. And the point is that we can use the exponential map to do that because we have Factoriality. Okay, so what does Factoriality mean in this case? Okay, so let me kind of show you what it means. Okay, so suppose you have a smooth group homomorphism between Lie groups, so phi from G to H. It's written in the bottom map here. Okay, so what you can also do is you can take the differential of this at the identity. Okay, so remember it maps the identity. It's a group homomorphism, so it maps 1 to 1. So we'll take the tangent space at 1 to G to the tangent space at 1 to H. Okay, so that's d phi 1. But this here, T1G, is just this Gothic G, and this tangent space I'll write as a Gothic H. Later we'll call these the Lie algebras of big G and big H. Okay, and remember there are exponential maps from these tangent spaces down to the groups. Tangent spaces down to the groups. Okay, which are local diffeomorphisms as well. And so you have this square diagram, and the point is it commutes. To go this way is the same as going this way. Okay, and that means that if you want to study this map, you can try to study this map first. Okay, and this is a lot easier because it's just a linear map. Okay, and we'll see that actually it will preserve a lot of structure in a later video. So let me just kind of intimate why this is true. Okay, so what happens? Okay, so let's start with something from here and show that it doesn't matter whether you go around this way or go around this way. What are the two ways of doing this? Okay, so we start with some vector inside there. Okay, we take that vector, which is something like that. Okay, so remember we have a corresponding left-invariant vector field and hence an integral curve through 1. So we're looking at 1 here, and a 1 on the H. Okay, the phi takes 1 to 1. And essentially this is your one parameter subgroup. You've got the phi v, your one parameter subgroup, maps from R to into this group. It doesn't have to be injective, but you'll get some sort of map like this. Okay, and now you can apply this group homomorphism. So this is a composite of groups, so you'll get here a group homomorphism from R to H as well, and that's going to be a one parameter subgroup as well that you'll get here. So what else do you have? Okay, so basically what you do, if you go around this way, okay, what you do is firstly you build this integral curve, okay, to this V, okay, and the left invariant vector field. You travel along it for unit time, and then you map it over to the other side. Okay, that's what you do. And so basically, it's you take the image of 1 here in here, and then you map it over here. So it's the image of 1 like that. Okay. What happens if you go over the other side? Okay, if you go over this other side, what you do is you first apply d phi to this tangent vector. So you map it over here. Then you build the left invariant vector field. Okay, and then you look at what is the integral curve here. But it's quite easy to see that, because this is a group homomorphism, it will take this integral curve to an integral curve which is also left invariant. Okay, so that's the key point. Because this is a group homomorphism, it preserves all the structure that you need to preserve to get to define the quantities the way they're meant to be defined. So basically, this integral curve that you use to evaluate the exponential map for this d phi of v is precisely just the image under phi of this integral curve, which means that here you also just look at the image of 1 inside here. And that is essentially the explanation for why this diagram commutes. And this is the diagram that will help us study Lie groups. Okay, so there's a lot more to the story, and in fact in the next video what I want to show is there's extra structure on this tangent space. So this tangent space here to 1 at a Lie group, it's called the Lie algebra of G, and of course you know that this tangent space captures the infinitesimal information about the geometry. But what it hasn't captured so far is what about the group structure on G? Okay, so remember, Lie group is essentially something which is both a group and a manifold at the same time. So you've recorded the infinitesimal structure of the manifold, but what about the infinitesimal structure of the group multiplication? And we'll see what happens is that you can put more structure on this tangent space to try to remember some of the group multiplication, at least infinitesimally, what is happening at the identity. I hope you enjoyed this adventure in pure mathematics.